Hello, it's a pleasure to be here. This presentation belongs to a IMS 2021 workshop dedicated to calibrated test beds for the characterization, optimization, and linearization of multi-input power amplifiers. The workshop is chaired by Apolinar Reynoso Hernandez from CSESI and Karun Rawat from the Indian Institute of Technology, Roorkee. This presentation is the second talk of the workshop and is entitled Calibrated Multi-Pore Large Signal Measurement Setups for Outphasing, Doherty, and Load-Modulated Balanced Power Amplifiers. My name is Thibault Reverand and I work at the EXLIM Research Institute. EXLIM is a joint institute of the University of Limoges in France and the French National Science Research Center, also named CNRS. My current area is RF instrumentation for nonlinear devices, and I will give you a talk about multi-pore large signal measurement setups. This talk will include bench setup, calibration algorithms fully detailed, and of course application on three kinds of RF power amplifier, outphasing architectures, Doherty, and also the more recent load-modulated balanced power amplifiers. This presentation won't be possible without my colleagues on this topic, Pierre Medrel and Jean-Michel Nebus at EXLIM, but also Zoya Popovic from University of Colorado at Boulder. First, let's talk about the main challenges in RF power amplifier design. Those PAs are dedicated for RF transmitter, and according to the digital market, the customer needs to apply more complex and broadband communication signals. If you work at the system level, you will focus on creating digital modulation optimized on a very high spectral density. Thus, the digital communication signals are associated with their analog complex envelope that includes both amplitude and phase modulations. From those complex envelopes, we can define some criteria like the peak-to-average power ratio, or PIPR. That is the ratio between the maximal instantaneous power and the mean power of the complete sequence. The probability density function, or PDF, that offers a statistic instantaneous peak-to-average profile, and the complementary cumulative distribution function, or CCDF, that give you the probability to get an instantaneous peak-to-average ratio higher than a threshold. Those statistic criteria are known by RF amplifier designer and can help them to optimize their design for a final application involving such digital modulations. The figure you can see here represents the normalized instantaneous power distribution with a 4G LTE signal. You can see there that the average power is 0 dBm because it has been normalized, and the maximum instantaneous power leads us to a PIPR of 10 dB. To use a RF power amplifier with this kind of signal in a RF transmitter, we have to ensure that the 1 dB compression point is located around the maximal instantaneous output power. Then a standard PA will be very efficient at this instantaneous power, as it is illustrated with the red curve. But the efficiency drops as the output power drops. If we consider a large sequence of the LTE modulated signal, as illustrated with its probability represented in the black histogram, you can see the global efficiency will not be good with a standard PA approach. Thus, it is difficult to transmit such a signal with high efficiency transmitters. Consequently, we have to design power amplifiers that exhibit a good efficiency over a large power backoff, as illustrated with the green curve. To make it possible, we have several power amplifier architecture candidates, based, for example, on dynamic load modulation that will exhibit an efficiency curve similar to the green one. We have, for example, the envelope tracking, the Doherty, the Kirex, and the load modulated balance, also named LMBA, power amplifiers. In this presentation, I will illustrate some measurement results on Doherty outphasing and LMBA devices. I will briefly discuss these three architectures right now. The Doherty amplifier, commonly used for power emitters, consists of two amplifiers, a main or carrier and an auxiliary or peaking. The auxiliary amplifier is usually biased in class C, which will offer a dynamic load impedance variation on the main amplifier. The output combiner sums the output power of the two amplifiers, which are not isolated. The combiner is based on a quarter wave line, making this topology a pretty narrow band. This structure can be digitally controlled. In this case, the input combiner or power splitter can be managed dynamically and digitally. In this case, the digital Doherty amplifier is a dual input power amplifier. The input and output port of this digital PA are represented in red. So, one input is associated with the carrier amplifier and the second one with the peaking. In order to optimize this dual input structure, a digital control of the amplitude and phase of the RF signals present on these two input devices would allow us to extract automatic control laws in the context of a given scenario for the amplifiers. The load-modulated balance amplifier, or LMBA, can exhibit the Doherty effect on the efficiency, but on a larger frequency bandwidth, by using two 3 dB 90-degree couplers as input and output combiner for a system presenting two identical balance amplifiers. Thus, the main amplifier consists of two main amplifiers biased at the same voltage, usually in deep class AB. The load modulation will be created by an external auxiliary amplifier connected at the control-in reference plane. The auxiliary amplifier will generate the signal in order to apply a dynamic variation of the load impedance depending on the magnitude and phase compared to the output power generated by the two identical and balanced main amplifiers. This injection of modulation, unlike the Doherty, is here perfectly isolated. There is no mutual load pull effect between the main and auxiliary amplifiers. We can see the LMBA architecture as an active load pull integrated system. Like the digital Doherty, we can define a digital LMBA, or dual input one, where the two inputs are the main input and the control in. The single output is the RF out. Those three ports are represented in red. The complete characterization of the two balance amplifiers as a dual input can lead us to the best configuration design for the auxiliary PA to connect to the control-in port. In the very first paper dedicated on the LMBA, we can see the best control law in terms of signal injection in magnitude and phase in order to improve the global efficiency of our large back-off. The outphasing approach consists of using the RF power amplifiers at a constant RF power. The RF power corresponds to their peak of efficiency. Thus, the input modulated signal, modulated in both amplitude and phase, has to be converted in two-phase only modulation at the power selected for the best efficiency. A combiner at the output rebuilds the desired amplitude and phase modulation as a two-complex vector addition. Two kinds of output combiner can be used. An isolated one, where the instantaneous undesired power is dissipated in a 50 ohm, and a non-isolated one. With the isolated combiner used in every link system, link stands for linear amplification with nonlinear component, each PA is loaded with a 50 ohm. But if the combiner is not isolated, it is then a Kyriax amplifier. Each PA will affect the other one in terms of load pull. So it is possible to design the best non-isolated output combiner from individual PA load pull measurement and to compare the performances of the complete system with a conventional isolated combiner. In this presentation, I will present the internal mutual load pull effect from measurement. It has been possible by including bidirectional couplers into the output combiner and connecting the couplet ports to a 4-port LSNA. In this presented case, the final measurement are then two inputs in red connected to LSNA, 2 internal output in red connected to LSNA also, and the main output of the system connected to a power meter. And the 3 kinds of power amplifiers I've told you about, we have seen that a digital control offers a degree of freedom. Then it is possible to reach the best efficiency of the system, for example. Therefore, multiple large signal measurements are essential to analyze accurately the next generation of power amplifiers. This tool is important to select a trade-off between linearity and efficiency, to improve RF modeling and design, and of course to extract dynamic law on linearity and then to implement the best possible digital predistortion. There is a need for multiple calibrated nonlinear RF measurements. And this presentation is about it. About setups, but also calibration method to apply on multiple large signal measurements. In this framework, we can consider 2 main kinds of measurements. Your measurements can be scalar and performed with power meters. But if you own an NVNA, you can extend your system to a multiport one. And in this case, calibration may be time-consuming, and I will present a new calibration method faster than commercial ones. For each kind of measurement setup, I will detail the calibration algorithm and present some final application on dual input amplifiers, such as digital Doherty, outphasing, and load-modulated balance amplifier. First, I will talk about multiport power meter-based measurement. For CW characterization, where power is usually measured using a simple power meter, we will see that, in one hand, the use of either a single source associated with a power divider of VSG synchronized with a local oscillator is mandatory for the characterization of multi-input devices as massive MIMO system or dual input amplifier. I will name the state synchronized RF source a multi-channel source. On the other hand, a calibrated multi-channel source provides a measurement of the relative phase between its channels. Therefore, it is not necessary to use an NVNA for multi-input device measurement. An application dedicated to large signal characterization will also be illustrated with dual input RF power amplifiers measurements that are a digital Doherty and a load-modulated balance amplifier. Let's talk about a one-pore single-source calibration for CW power meter-based measurement. The RF source is a VSG. The CW output frequency is the local oscillator 1 when the complex envelope is constant in the time domain. When the source is not calibrated at the reference plane, displayed in red, the input power command is consistent with the available power at the RF generator coaxial output connector. If the source is calibrated in the framework of a complete setup, then its reference plane is not necessarily the coaxial output of the instrument, but can be the reference plane of the measurement bench. Thus, the source includes the power driver. The power calibration is very simple. It consists of using the calibration standard, that is the calibrated power probe. By connecting this probe at the bench reference plane in red, the available power at the plane of the device under test, named P dot, is obtained. We also know that the available power claimed to the instrument and named P source. The difference between these two powers is delta P and gives us the gain of the chain placed between the instrument user interface and the bench reference plane. This calibration can be performed for all the frequency of interest. This table of delta P as a function of the frequency will allow the user to enter the desired available power in the reference plane P dot to a program that will automatically calculate the source power P source to assign to the instrument. For modulated signal calibration, 2 other calibration steps are required. A CW sweep in the envelope bandwidth for amplitude calibration with a power sensor, and then a multi-tone characterization with a VSA for the phase calibration. This presentation here only presents CW measurement calibration. If you are interested in the complete two-tier calibration method, adding modulated signal capabilities, I will give you the corresponding reference to read at the end of this presentation. if you want to measure a device with multiple input, the idea is to stack VSGs and ensuring phase coherence between them. This requires synchronization of the trigger and the local oscillator. The trigger, represented in green, will synchronize the starting time of envelope associated with a modulation. Using the trigger will force the envelope delay to 0, but the RF carrier should be synchronized as well. That's why a local oscillator, represented in blue, and the VSG has to be indeed a single and unique common reference signal. I am naming multiple source a stack of several VSGs, perfectly synchronized both with trigger and local oscillator. Notice that you can create a low-cost CW multiple source with a single RF generator, so the local oscillator, associated with an N-way power divider and some step attenuator and phase shifters. In the system, the source number 1 has already been calibrated in an absolute way by a one-port calibration method previously explained. All other sources will be fully and automatically calibrated thanks to an N-way power divider previously characterized as a SNP file. A calibrated power meter sensor is connected at the output of the multiport power divider. This pre-characterized multiport passive circuit is then our calibration standard. During the automatic calibration procedure, the source number 1, already calibrated, will be active. Other sources will be calibrated sequentially. Only source number I will be active. The calibration signal is a single-tone CW. During the calibration, both VSG number 1 and I will generate a constant time domain complex envelope. The phase of this complex envelope will be arbitrarily set to 0 for the first generator. The phase of the generator I will be controllable, either by delta phi, if this input is available in the VSG, or by a phase offset of the complex modulation data in the frequency domain. To measure the error terms of the calibration, we sweep the frequency within the frequency bandwidth of interest. This sweep is performed by the local oscillator. Since only two sources are simultaneously active during calibration, the other sources can be considered as a 50 ohm impedance. This is ensured by the use of circulators just before the reference plane. Here, the source number I will be calibrated. And to calibrate the complete multi-source system, the variable I value will be changed from 2 to n-1. The benefit of our calibration method relies on the use of a single standard, a pre-characterized passive multiport device that ensures traceability from a metrological point of view. Let's see more details about this sequential calibration. The source number 1 is already calibrated, so the power wave at the reference plane A1 is known. To be more precise, A1 can be measured in CW by an input power meter connected to a directional coupler at the input 1. At the output of the multiport standard, the BN wave is also known in magnitude thanks to output calibrated power sensor measurement. The wave AI, located at the bench reference plane I, is unknown. It corresponds to the signal requested by the user at the source number I in amplitude in phase. The user command at the VSG reference plane can be calculated as a power wave noted ASI. ASI is the input command power wave of the source number I. AI is the output power wave of the same source, and GI is the complex gain or calibration error terms for the source number I. Thus, we have AI that is equal to the command, so ASI, multiplied by this gain, GI. And we have to find out GI in magnitude and phase. Let's go back to the passive multiport. By definition of its matrix, we can express Pn as a function of A1 and AI. However, only the amplitude of Bn is known from the CW measurement with the output power sensor. According to the definition of the passive multiport S parameters, we get the following expression. Pn is equal to Sn1A1 plus Sni-AI. In terms of power, it becomes a quadratic equation of the magnitude of Pn. This quadratic equation can be developed in a linear form of which the unique unknown is the complex gain Gi. This is the error term of the system for the source number I. To find Gi, that is a complex error term for source calibration, we have to solve a real linear equation system with three unknowns, the magnitude of Gi and its real and imaginary parts. To this system of equation, we need three independent measurements made with three different values of RSI, which is the power wave in magnitude and phase of the source I, user control. Therefore, we will consider a minimum of three distinct values for the phase of ASI, named delta phi. Here is an example of three values, phi A, B, and C. The three real values that are the magnitude, the real and imaginary part of Gi are then obtained by inversion of the matrix representing the linear system. It is possible to consider a large number of independent phase values for the calibration. In this case, the phases for ISI may be valued uniformly distributed between 0 and 2p on a number of phases specified by the user. The matrix inversion will be done by the pseudo-inverse operator and will lead to the solution of Gi in the sense of least square. This concludes the calibration procedure, which is applied in CW mode for each frequency of interest and each source port to be considered. This is an absolute calibration in magnitude and phase consistent with VSG number 1 already calibrated in one port. Now that the source is calibrated, we will proceed to a verification of this calibration on a passive device. In our case, the two synchronized VSGs are a single two-output instrument, the Rode-Schwarz SMW200A. Each of the channels is associated with power drivers in order to feed correctly later dual input power amplifiers during large signal measurements. So first we measure a power combiner. The idea is to vary the value of delta phi and measure P out. The input power is given by power meters. Here we will validate the phase calibration of our multi-channel source by comparing three results. A blue curve will represent P out versus delta phi when there is no phase calibration. Delta phi is then the value directly entered into the instrument. A black curve will take into account the phase calibration. The delta phi is the phase at the input reference plane. It is calculated from the phase of Gi and the phase of ISI. And finally, a reverse simulation will be illustrated in red. Delta phi is calculated from the measured P out, the S parameter of the combiner, and the measured input powers. And here are the results obtained for 7 different RF frequencies. The uncalibrated system is well repeatable, but does not take into account the relative time group delay between the two RF inputs of the combiner. The multi-port calibration proposed here includes a relative phase calibration and brings us to the results similar to what we obtain in simulations. Now we will use our magnitude and phase calibrated setup for parameter-based large signal measurement on dual input RF power amplifiers. First, I present a digital Doherty amplifier under large signal CW measurements. The main input is at the top. Therefore, we measure P in and P out with coupled power meters. For each main input power value, the auxiliary input power waves value located at the bottom should be swept in magnitude and phase. We consider two variables, delta P and delta phi that correspond to the power and phase difference between the two inputs. The measurement can be done at several frequencies. For each P in, delta P and delta phi, we have a payout, and we have different consumption and therefore PIE value. The idea underlying this measurement is the extraction of an optimal control law to obtain the best possible Doherty amplifier input combiner. Here are some measurement examples at 2.3 gigs. The gain, that is P out over the sum of the input powers, and the drain efficiency, P out over PDC, are represented. Each dot in gray corresponds to a unique measured combination P in delta P delta phi. From this dataset, it is possible to extract the optimal curve according to the power added efficiency. Each power point of the red curve corresponds to the best efficiency over 7 dB backoff. Extracting the value of delta P and delta phi for each power leads us to an optimal control law in efficiency of the measured digital Doherty amplifier. Performing the same approach on a gain as flat as possible over our largest power range will define another control law for delta P and delta phi on the green curve. This curve is an optimized behavior for the digital Doherty in terms of linearity. This kind of information may allow the design of optimal digital power driver to be located at the input of the measured digital Doherty. The second practical case is illustrated here. This is a load-modulated balance amplifier, or LMBA. The idea of this type of amplifier is to use two identical primary amplifiers. These amplifiers are embedded with two 90-degree 3 dB couplers used as a divider for the input and a combiner for the output. The main input, labeled output, corresponds to the port where the power of the two power amplifiers is combined. The main input is the port named input 1. The principle of LMBA is to create a dynamic variation of the load impedance of the mains as on a Doherty, except that here there is two mains, and the load pull effect is made by the injection on the port named input 2. Compared to the Doherty, we are here on an isolated system. There is no mutual load pull effect between the mains and the auxiliary amplifier to add in the system. We perform the same kind of measurement than with the digital Doherty. A power sweep is applied on input 1 port. For each available power, two other sweeps are performed in magnitude and phase on the power wave at the reference plane input 2. For each combination of P in, delta P and delta phi, we measure P out, the PIE, and so on. This slide presents a measurement example at 2.4 gigs for an available main input power of 28 dBm. This surface represents our measurement result on the plane delta P and delta phi. The measurements are made with a step of 2 dB for delta P and 15 degrees for delta phi. The black outlines represent the output isopower curve of the LMBA. The colored gradient are the result in terms of PIE. The load pull effect created by the injection at the second input of the LMBA is directly observed with simple power meters. We note the injection level in magnitude and phase leading to the optimal value for PIE or output power. This graphic representation therefore encourages us to select the best power wave in magnitude and phase to inject at its second input. The coordinates of this point are then directly the IMM and MPM characteristic of the RF auxiliary channel to be added in order to transform this two-input LMBA into a conventional single-input amplifier. This concludes my talk related to the parameter-based measurement. The second part of this presentation is dedicated to vectorial calibration and measurements for multi-port nonlinear devices. The final application presented here will be the internal waveforms measurements to validate the load pull effect on an out-phasing power amplifier. Then I will propose a new algorithm to reduce the calibration time of a multi-port NVNA. For outphasing RF power amplifier, we have two equal main amplifiers, MMIC PA1 and 2 on this slide. These PA are always driven in power saturation at a constant and unique average input power. The value of this average power ensures the best efficiency of those PAs. Because the final application of the complete PA is to be efficient with modulated signal, we have at the input a signal component separator that transforms in a Fresnel plane an amplitude and phase modulation dynamically into phase modulation. Each internal PA is always efficient because it's driven by a fixed amplitude selected according to the maximal PAE. Then you can combine the two outputs with an isolated or non-isolated combiner. The isolated combiner is a standard approach in Link application because it's easier to design. Link stands for linear amplification with nonlinear components. The non-isolated combiner is more interesting because the individual power amplifiers see each other, creating a output effect internally of the complete outphasing PA. It is more complicated to design such a combiner, but an investigation in this approach is interesting. So, we did an experiment to see what's happening in such configuration. We took two MMIC, 3-rate PA. In the photograph there is one of our PAs, and we put it together in a system where the combiner can be isolated or non-isolated, and we can compare the performances. So, we first measured each of the MMIC amplifiers separately, did some load pull, and found what the impedance is at function of the outphasing angle. So, those load pull measurements are the foundation of the simulation required during the non-isolated combiner design. As you can see on the Smith chart, the 0-degree outphasing angle corresponding to a maximum output power is matched on the highest PAE impedance. Other outphasing angles leading to lower output power will change determination of the MMIC PA1 and 2, as illustrated here by the orange and green circles. To make internal measurement on the complete outphasing PA, we have transformed a standard 2-port LSNA in a 4-port system thanks to our RF switch matrix. Notice that the output directional couplers are part of the output combiner and were of course considered during the design. The S parameters of those couplers have been taken into account for the designing of both isolated and non-isolated combiners. To perform 4-port measurement, we have considered 3 status of our 2-port LSNA. For each switch configuration, we have a 2-port LSNA calibration file and measurement. The 4-port measurement are then performed sequentially. Phase coherence is possible thanks to port 1 that is always measured and is our phase reference. Because LSNA came with only 2-port system calibration, we are using conventional 2-port SALT for LSNA 3 times. We will see later how to improve this and currently available commercial NVNAs. You can see here the bench used for outphasing characterization. The idea here is to control the power injected at the top amplifier. Then we adjust the power at the bottom amplifier to ensure the balance with the top amplifier, and a phase shifter at the input of the bottom amplifier will exhibit the outphasing angle behavior. Waves measured at the output of the MMIC PAs make it possible to visualize the output effect created by the outphasing angle. A power meter at the final output indicates the output power of the complete system. We have done such measurements for both isolated and non-isolated combiners. Here are displayed the measured internally load modulation. Results with the non-isolated are displayed on the Smith chart at the bottom right, and the isolated combiner results are on the top. You can see also on the left the benefits of using the non-isolated combiner over the isolated one in terms of efficiency over the output power backoff. Multi-port large signal measurement can help to improve the design and the validation of the output combiner in this outphasing amplifier example. And of course, you can make the same measurement for several bias points applied to the MMIC PAs. Here presented the global efficiency of the system when you consider an asymmetric multi-level outphasing. You can directly extract the best efficiency performance of the RF module and the expected backoff for configuration in envelope tracking. This concludes the example of a multi-port NVNA measurement on an outphasing amplifier. My talk will deal with the extension of a currently available nonlinear network analyzer, or NVNA, from 2 ports to multi-port configuration. Due to the large number of ports, short open load through and short open load reciprocal, or unknown through, calibration may be extremely time-consuming, as several true calibration steps are required. In this presentation, we will see how to perform a SALT or solar calibration with a passive and then reciprocal multi-port through structure. The principle of nonlinear VNA or NVNA is to use a VNA not to measure the waves ratio like reflection coefficient or S parameter, but to measure A and B waves. Typically, NVNA users have 2-port NVNA based on the use of 4-port VNA, including 2 independent RF sources. I have represented here a 2-port NVNA system from Rode-Schwarz VNA and a user-defined test set. Here, port 1 and 2 are associated with the RF source generating the DUT signal. Port 3 and the second independent source are dedicated to the reference COM generator, or HPR for harmonic phase reference. So you need a 4-port VNA to create a 2-port NVNA. There is 2 options to increase the number of ports on a NVNA. The simplest but also the most expensive method consists on using a VNA including a large number of direct receiver channels. The other solution consists on building a switch matrix in order to create additional ports associated with a single port on the initial VNA. The need for a multi-port NVNA is associated with the characterization and validation of new multiple input-output nonlinear RF circuits. We saw in the previous slides some application on digital Doherty and load-modulated balance amplifier, but large signal measurement of beamformer circuits require a multi-port NVNA. This comes with the emergence of phase array antennas. Now that a multi-port NVNA has been presented, I will focus on its calibration. Let's start with the 1-port relative calibration of a VNA or NVNA. For this purpose, we measure 3 perfectly known gamma standards: gamma short, open, and load, and 3 uncalibrated measurements for those standards: gamma M for short, open, and load. From those 3 measurements, we can solve the linear system, leading us to the 3 error terms related to the measurement port number I. An absolute calibration means we got 4 error terms, but with a short open load, we have performed a 1-port relative calibration, leading us to only 3 error terms: beta prime, gamma prime, and delta prime. This calibration is incomplete. If we consider alpha is equal to 1 for this calibrated port, we will say that the system is partially calibrated. Traditionally, the calibration of a 2-port NVNA is based on the relative calibration applied to each port of the NVNA. Thus, 3 error terms are allowed to correct the uncalibrated waves A1M, B1M, for example, measured by an NVNA port in order to calculate the gamma in the reference plane, where waves A1 and B1 are illustrated. The second port is calibrated with short open load as well to identify error terms beta 2, gamma 2, delta 2. To ensure correct transfer gain measurement, a transfer calibration is performed with a true standard depicted in green on this figure. This true calibration makes the port 2 calibration absolute and complete. This absolute calibration is consistent in magnitude and phase with port 1 calibration. To get an absolute calibration of port 1, we need 2 standards to calibrate the wave A1, 1 in magnitude and 1 in phase. This final absolute calibration leads us to the final error term alpha 1. Remember, as I said on the previous slide, the short open load calibration leads us to a partially calibrated system. For example, by applying this incomplete calibration, our port 2 can measure gamma properly, but the gain between port 1 and 2 won't be correct. In order to make every port of our system consistent in magnitude and phase with the measurement performed for 1, we will proceed a true calibration, either SALT if the true is totally known, or a SOLAR if the true circuit is unknown. This true calibration will identify the value of the fourth error term, alpha I, for the port number I. With a multi-port NVNA, the calibration procedure remains the same. First of all, we have to calibrate each individual port in short open load. Then, the true standard must be applied between ports. The approach right now and available in commercial VNAs consists on performing n-1 time the two-port calibration method between port 1 and each other port. The presentation right now proposes a theory and application on how to use a multi-port through in order to calibrate a NVNA with a large number of ports in one shot. If this multi-port is passive, it will be reciprocal. Both SALT and SOLAR method can take advantage of such new standards. So from now, I will call A bar and B bar the partially calibrated measured wave. Usually with the SALT algorithm in two-port, we assume to already know the S2P of the true device used during the calibration. We assume that alpha 1 is equal to 1 and then A1 is equal to A1 bar. Then we can write easily the wave equality equation, that is B2 is equal to S21A1 plus S22A2. That is valid during the forward mode measurement. By substitution with partially calibrated data, I mean A bar and B bar, we can easily identify the value of alpha 2 to make the port 2 consistent with port 1. Generalizing the two-port equation to a multi-port measurement system leads us to a matrix form equation that is displayed here. Thus, SALT forward calibration of a multi-port NVNA can be performed in the following way. The signal is active on port 1 only, and the waves are measured on all ports. As we are in the SALT method, the SNP calibration standard is assumed to be perfectly known. Obtaining the terms alpha 2 up to alpha n is given by the same equation than before, but generalized to multiport. Now that we have presented the SALT method for NVNA, in the multiport case, we'll now deal with the SOLAR method. The SOLAR method, which stands for short open load reciprocal, does not require the complete knowledge of the calibration standard through. It is just mandatory for the standard to be reciprocal, which is the case when the circuit is passive. This method has been proposed in 1992 by Andrea Ferrero and his colleague Pisani on a two-port VNA. Here we will not only deal with the SOLAR in the NVNA calibration formalism, but also generalize it to multiport. The SOLAR method assumes that a true multiport calibration device is reciprocal. In terms of S parameter, this means that Sij is equal to Sji. It is this assumption that will lead us to the identification of the error terms alpha 2 to alpha n, as we have done with the multiport SALT method. The difference here is that the active source will successively be port 1, 2 until n. For each active source position, all of the waves A and B are measured. This wave A and B can be represented in matrix form with matrix A and B. Bij, for example, corresponds to the wave B measured on port I when the active source is on port J. From these matrices A and B, the S-parameter matrix of the device under test is given by matrix B multiplied by the inverse of matrix A if the waves A and B are fully corrected by error terms extracted from a full calibration. So, if the system were fully calibrated, we would have S is equal to B multiplied by the inverse of the matrix A. but after a short open load applied to every port, we are dealing with a partially calibrated system. With such an unfinished calibration, we can measure S bar, and the relation between S and S bar is linear. Because we know by assumption the standard device is reciprocal, we have one more equation, that is Sij is equal to Sji. This equation leads us to alpha j equal to plus or minus alpha I square root of the ratio of S bar measurements. There are two solutions. The correct solution is selected according to an estimation of argument of Sij. Practically, we'll start from alpha 1 is equal to 1, then we calculate every alpha I for I is equal to 2n. But there are a large number of measurements that make the identification of alpha I possible. That's why we will use a sorting algorithm that considers only the best measurement to calculate the error terms, the Dijkstra algorithm. I'm going to show you how it works with an example on a non-ideal 4-port true calibration standard. This standard is 10 dB directional coupler, which has been unbalanced by adding a 3 dB attenuator on one of the couplet ports. This device has a strong isolation between port 1 and 4, as well as between port 2 and 3. It is therefore not ideal, and it's hard to imagine calibrating an NVNA with a multi-port salt method with such S41. During the solar calibration, all the measurement configurations are measured. Then only the largest value of Sij bar of interest are considered for the calculation of alpha. So we start from port 1, with alpha 1 is equal to 1. From this port 1, we have three possible RF paths going respectively to port 2, 3, and 4. The path representing the minimal measured losses is the path connecting port 1 and 2 in this example. So this RF path is therefore selected, and the measurement S12 bar and S21 bar are used to calculate alpha 2. So now we have two known nodes in our diagram, 1 and 2. Starting from known nodes, 1 and 2 in red, we are going toward unknown nodes 3 and 4. 4 RF paths are possible. The path representing the minimal losses, in this case, is joining port 1 with port 3 and correspond to 10 dB of attenuation. This RF path isn't selected. S13 bar and S31 bar are considered to calculate alpha 3, and the node number 3 is known. It remains to identify the missing node starting from one of the three known nodes. The RF path presenting the minimal losses consists in starting from number 3 to go toward 4 in this example. Alpha 4 is then identified from measurement S34 bar and S43 bar. The diagram is complete. All error terms related to a true were identified. This concludes the multi-port through calibration of our NVNA. We just have to test our SALT and solar multi-port algorithm. We will compare 4-port measurement of S parameter made with a commercially available multi-port calibration, a classic solar, and the new calibration method proposed here. The classic solar calibration of the through is carried out in 3 steps with a direct 2-port transition. SALT and solar multi-port calibration will be tested with a T standard presenting few losses, noted standard B here, and a non-ideal standard presenting high isolation, standard C. The calibration comparison will be done on device B and C as S4P measurement from an NVNA calibrated in solar, and S4P measured by a commercial VNA. The comparison of S parameter helps us to conclude on our new SALT and solar method. First, if your multi-port through standard does not have a lot of losses like our standard B, SALT and solar method show very similar result. SALT is extremely fast, only 1 forward measurement during calibration, but require an accurate S parameter of the standards. If your standard presents some losses or isolation like our standard C between port 1 and 4 or 2 and 3, the solar method is pretty robust because the less lossy RF path will be selected in our algorithm in order to calculate the alpha error terms. But the SALT with a lossy standard destroys the consistency of the measurement, even if the S parameter of the standard are known. Here, the slide presents the architecture of the multiport NVNA as implemented in LabVIEW. First, a port object includes its own CalKit and RF switch matrix configuration. It enables easy measurement of hybrid devices. At the end, the multiport NVNA is an array of those predefined ports. The user has to calibrate each port in short open load, then it is possible to calibrate in through the complete system. The user will have to consider a SNP file that contains the S parameter of the standard installed or an estimation of the phase transfer for the solar. The number of ports is unlimited. Now it's time to conclude. Two kinds of large signal measurement have been presented. A scalar one based on power sensor only, and a vectorial one based on NVNA. Regarding the power meter setup, a new multi-source calibration method has been proposed. This calibration could be totally automated. It requires just a pre-characterized multi-port passive device. This method has been analytically detailed and experimentally validated. Then, large signal measurement on dual input RF power amplifier have been presented. We have seen such calibrated measurement offer a unique experimental view to optimize the design of drivers dedicated to dual input amplifiers. The second kind of setup is based on the user NVNA. Large signal measurements on a hot phasing amplifier illustrated the interest of this bench. Finally, two enhanced calibration methods optimized for multiport NVNA have been presented. The new multiport salt and solar algorithms were detailed and validated. Notice that the salt and solar methods are less time-consuming than procedure embedded in commercial VNA right now. These benches and calibration methods of multiport devices are prima of importance for MIMO systems as dual input power amplifiers, beamformer dies, or large signal phase array antenna measurements. Furthermore, I present to you in this slide the three main references corresponding to the three parts of the work presented here in the framework of this workshop. Thank you for your attention.